I want us to, in this session, to look at calculations of electrolysis. In most of these calculations, we are going to be using Faraday's first and second laws. And I'm going to do a number of them. I have my first question as this one. Calculate the quantity of charge required to deposit 40.5 grams of aluminium during electrolysis of a solution of aluminium ions. You're told that 1 Faraday is 965. Even if it's not given to you, you should be knowing it. And then aluminium is 27. That's the question that we do have. What's the solution to that question? The question wants us to get quantity of charge. Quantity of charge is Q. Which mass are we given? Mass is 40.5 grams. Which law of electrolysis are we going to use here? Both laws will be used, but most importantly, the second law, Faraday's second law of electrolysis, is most applicable here. What do I expect you students to do? I expect you to first of all write equation for what they are talking about. We are depositing aluminium from aluminium ions. So aluminium ions are depositing aluminium metal. This is balanced by writing 3 electrons here. Then we should know the relationship between electrons and charge, or we should know the purpose of this. Are we together? And then we should know that this is 1 mole of aluminium being deposited by 3 moles of electrons. 3 moles of electrons are equal to 3 Faraday. 3 Faraday are equal to 3 times this quantity of charge. And 3 times this quantity of charge is depositing for us 27 grams of aluminium. How about the 40.5 grams they are talking about? So I expect you to begin by saying that, look at this, you say 3 moles of electrons deposit 1 mole of aluminium. That's according to this equation. But we are given Faraday's constant. So that means 3 Faraday. I'm doing it from first principle, but you learn to go direct. 3 Faraday deposit 1 mole of aluminium. That means that 3 times 96500 coulombs deposit 1 mole. Actually, let me turn it into mass because we are going to deal with mass. 27 grams of aluminium. So, are you getting me up to that point?
No, teacher. I've just joined and I don't know even where we are.
Yeah, you missed the beginning of Faraday's laws of electrolysis. So we have that column, those columns of charge depositing 27 grams of aluminium. Now we ask ourselves, how are we going to relate with this mass they are talking about? That means I have to do some arrangement and change the way I'm writing this. I will say 27 grams of aluminium are deposited by 3 times 96500 columns of charge. How about the 40.5 grams they are talking about? 40.5 grams are deposited by 40.5 times 3 times 96500. We are cross multiplying, divide by 27. When you do the simple mathematics here, you get 434,250 columns. So that's the quantity of charge that they wanted you to calculate. What does this mean? This means that you may not have to write all this. If you have space, you may write all of it. But if you have a way of avoiding all that, you may go direct here on this third step here and proceed by your calculation. That's example 1. That is example 1. I think I can now proceed to the second example. In my second example, I have this question. It says, when a current of we don't know the current. So when a current is passed through a silver nitrate solution for 10 minutes, .54 grams of silver was deposited at the cathode. Calculate the current. These questions are very simple. They involve both Moore concept and Faraday's laws. And the moment you master the two, then your work becomes simple. Allow me to make a simple summary here. We don't know the current. We are given a mass deposited, 0.54 grams of silver. We are given the time, 10 minutes. But I told you, my dears, that when we are dealing with Faraday's laws, mass should be in grams, time should be in seconds, and current should be in amperes. So which relationship do we have between I and T? We need to get the quantity of charge first of all, and then you relate. You remember this relationship. Quantity of charge is IT. We have the time, we don't have the current. And it's the current that they want. So our I will be Q over T. We have the T, but we don't have the Q. That means we need some information that will help us get the Q. And that information will involve this mass. It takes us to Faraday's second law, which says that the quantity of charge, remember that law, it says the quantity of charge passed through an electrolyte that is required to liberate 1 mole of an element is proportional to the charge number of its ion. So that implies that I need to write the equation that leads to deposition of silver. That is the silver ion giving me silver metal. And this equation occurs at the cathode. What does this imply? It implies that 1 mole of silver is deposited by 1 mole of electrons. And 1 mole of electrons is 1 Faraday. Since we are dealing with mass, let's use molar mass of silver, which is 108. So 108 grams of silver is deposited by, convert the Faraday to charge, 96500 coulombs. How about this mass here, the 0.54 grams of silver? This is deposited by 0.54 times 96500 out of 108. And the answer you get from that is, the answer is 482.5 coulombs. That's your charge, Q. Now we bring your Q here, which is 482.5 over the time. The time is 10 minutes, multiply it by 60, convert it to seconds. And when you work out this very well, you'll get your I as 0.804 amperes. Shabla, are you now picking something?
Yes, teacher.
So that is our second example. If that is our second example, I want to do 2 or 3 more examples and then we call it a session. My third example is this. It says, determine the time taken. Determine the time taken to deposit 1.0 grams of chromium when a current of 0.120 amperes flows through a solution of chromium 3 sulfate. We want time. What do we do? The question wants to get time in seconds. We are given mass of chromium in grams, and we are given the current at 0.120 amperes. How do we get the time? Still, we should know that time is got from this expression, IT, and time will be UQ over I. So you have the I, but you have no Q. How do you get Q? Faraday's second law. Write the equation for deposition of chromium from chromium 3 sulfate. So that equation is this one. Deposition of chromium. Then make sure you begin with a statement that has mass, so that you get the charge, which you don't know. You know the mass, you don't know the charge. Chromium is known to be equal to, if you don't know, you always check the periodic table in paper 1. In paper 2, it may be given. If it's not given in paper 2, like last year, there was a question for the students to use relative atomic masses, yet they had no periodic table and the values were not given. You have to feel free to ask for a periodic table. So what do we have in this case? We shall say 1 mole of chromium is deposited by 3 Faraday. What does that mean? It means that 52 grams of chromium, which is 1 mole, is deposited by 3 times 96500 coulombs of charge. 1 Faraday is 96500 coulombs, but these are 3 Faraday. Now, how about 1 gram of chromium? 1 gram of chromium is deposited by 1 times 3 times 96500 over 52. So your Q will be the value you get from this. The value you get from this is 5567.308 coulombs. You substitute the Q here and get the time. So what will be your time? Time is Q quantum charge over I. The quantum charge is 5567.308. We have already got that. Divided by the current in amperes, which is 0.120, and the final answer is 46394 seconds. If they want you to convert it to minutes, then convert it to minutes. If they want it in hours, convert it to hours. I'm doing more examples. I think I should do one more example. And then we shall do some more higher order examples in our next lesson. So what is my next example? My next example 4, we shall have to do all the 10 examples that I have. And then for you, you'll have about 14 questions to attempt involving these calculations. My very last example for today's session is this one. It says, calculate the mass. Calculate the mass of lead deposited at the cathode during electrolysis when a current of 1.50 amperes flows through molten lead to bromide. For 20 minutes. Lead is 207. What do we have? They want the mass of lead deposited. We don't have that. The current is 1.50 amperes. The time is 20 minutes. Convert the minutes to seconds, multiply it by 60 to convert it to seconds, because here we deal with time in seconds. So we already have the current and time. That means we can get the charge, which is IT, and that is 1.5 times 20 times 60. It gives us which answer? The answer here is 1800 coulombs. That's the quantity of charge. So now, which mass is deposited by this quantity of charge? That's what the question wants us to get. Can we write equation for deposition of lead after electrolysis of molten lead to bromide? Note this, we are electrolyzing molten lead to bromide. So if we are electrolyzing molten lead to bromide, our equation should be equation at what? At the cathode. Because that's where lead ions will migrate. The lead to ions which are in liquid form, because this is molten lead, according to the question. It's not lead to bromide solution. Remember, lead to bromide is insoluble in water. So we cannot electrolyze it by dissolving it in water. We simply heat it to become molten. So this should be liquid lead, giving us lead metal. Okay. So if it's giving us lead metal, then we should add 2 electrons here. Add 2 electrons there. So if 2 electrons are depositing this mass, which is 1 mole of lead, okay? So 2 moles of electrons deposit one mole of lead. That implies that 2 times 96500 coulombs of charge deposit 207 grams of lead, which is 1 mole. How about the charge we have got here, the 1800? 1800 coulombs deposit, 1800 times 207 over 2 times 96500 grams. And the answer we get from this is 1.931 grams of lead. Thank you for attending this session. Subscribe to our YouTube channel for more of these lessons. We meet next time. Have a good day. Bye-bye.